Introduction. Hi Rohit, what are you doing? Did you read the news of Cobalt-60? No, what happened? The radioactive material Cobalt-60 was found in Mayapuri, Delhi West. I don't know. And what is radioactive material? It is a kind of material which emits radiation which is harmful for life. Okay, so what happened at Mayapuri? They found radioactive material, and a person was dead after getting in touch with radioactive material. That is very sad news. Over disadvantages, they do have favorable advantages. They are the bulk sources of energy. In this lesson, you will learn about the nuclear power generation. Objectives. At the end of this lesson, you will be able to define atomic mass, explain composition of nucleus, define size of the nucleus, state Einstein mass-energy relation, explain nuclear binding energy, explain nuclear force, explain alpha, beta, and gamma decay, find half-life of radioactive material, explain fission and fusion, and explain the nuclear reactor. Atomic masses and composition of nucleus. The number of molecules in 1 mole of carbon is 6.02 into 10 raised to the power 23. That is Avogadro number. Since carbon is monoatomic, therefore, there are 6.02 into 10 raised to the power of 23 atoms of carbon. They have a mass of 12 gram. Hence, mass of one atom of carbon is equal to 12 by 6.02 into 10 raised to the power of 23 gram, which is equal to 12 by 6.02 into 10 raised to the power of 26 kilogram. Hence, 1 atomic mass unit, AMU, is equal to 1 by 12 into 12 by 6.02 into 10 raised to the power of 26 kilogram whole, which is equal to 1.6605 into 10 raised to the power minus 27 kilogram. Atomic mass is conventionally expressed in atomic mass units, such that the mass of the most abundant type of carbon atom is, by definition, exactly 12 atomic mass unit. Composition of nucleus. Rutherford's experiment on the scattering of alpha rays led us to conclude that an atom has a tiny central hard core. Nearly the whole mass of the atom is concentrated in this core. This central core is named as nucleus. Every atomic nucleus contains basically two types of particles, protons and neutrons. The single exception is that of nucleus of hydrogen. This nucleus contains only one proton. The total number of protons in atomic nucleus is equal to total number of electrons in atom. So, the total amount of negative charge present in atom is equal to the total amount of positive charge in the atom. This makes the atom, as a whole, electrically neutral. The composition of nucleus can be considered as: let Z be atomic number, which is equal to number of protons. Let N be neutron number, which is equal to number of neutrons. Let A be mass number, which is equal to Z plus N, which is equal to total number of protons and neutrons. Nuclear species are shown by the notation, where X is the symbol of nuclear species. The atoms of an element having same atomic number, that is Z, but different mass numbers are called isotopes. For example, isotopes of hydrogen are Discovery of neutron. A is a disk having a radioactive source, polonium, which gives out alpha particles. B is the target of beryllium. Both A and B are placed in an evacuated chamber C. The beryllium plate issued out strong rays, which on falling at a block of paraffin gave out high-energy protons. The nuclear reaction for the production of neutrons is expressed as size of the nucleus. It has been confirmed by various experiments that the nucleus does not have a sharp or well-defined boundary. However, the nucleus radius r can be given by r is equal to r0 into cube root of a, where r0 is equal to 1.2 into 10 raised to the power minus 15 m is a constant, which is the same for all nuclei, and a is the mass number of the nucleus. Mass energy. Einstein gave the mass-energy equivalence relation. E is equal to mc square, where energy E is equivalent of mass m. C is the velocity of light in vacuum, that is 3 into 10 raised to the power 8 meter per second. Nuclear binding energy. Mass defect. It is found that the mass of a stable nucleus is less than the total mass of its nucleons, that is protons and neutrons. This difference delta m in mass is called mass defect and is given by delta m is equal to zmp plus a minus z into mn minus m, where mp and mn are the masses of proton and neutron respectively. M is the actual mass of nucleus. A is the mass number. Z is the atomic number. The energy equivalent to the mass defect, that is delta m into c square, is the binding energy, EB, of the nucleus. From the graph, we note that binding energy per nucleon increases with A, and after attaining flat maximum, it decreases gradually. Nuclei with intermediate mass number have highest energy per nucleon. For mass number 56, the binding energy per nucleon is highest. At a multiple of 4, that is corresponding to mass numbers 4, 8, 12, and 16, the binding energy per nucleon shows a sudden raise. This is particularly marked in the lighter elements. The average binding energy per nucleon is 8 MeV. For lighter and heavier elements, the binding energy per nucleon is less than the average value. Nuclear force. It is the nuclear force which binds the nucleons together and is responsible for the stability of nucleus. Properties of nuclear force. They are ordinarily attractive. They are charge independent. They are short-range forces. They are spin dependent. They are non-central forces. And the nuclear force is the strongest of the three fundamental forces that are gravitational, Coulomb, and nuclear force. Radioactivity. Unstable nuclei can often transmute into other nuclei through the emission of alpha, beta, or gamma particles. Any such spontaneous transition from one state to another is known as a radioactive decay. There are three types of radioactive decay: alpha decay, beta decay, and gamma decay. Law of radioactive decay. If n denotes the number of radioactive nuclei of any specified type at a given time, and lambda is the constant probability for decay per unit time, that is, decay constant, then the change in the number of nuclei during an infinitesimal time interval dt is defined by dn is equal to n t plus dt whole minus n t, which is equal to minus nt lambda dt. The negative sign indicates that nuclei decreases as a result of decay. Let n naught be the initial number of nuclei at t is equal to 0. Then nt, that is number of nuclei at any time t, is written as nt is equal to n naught into a raised to the power minus lambda t. Let r be the decay rate, which can be defined as r is equal to minus dn by dt. Name it as equation 1. Differentiating equation 1, we get r is equal to lambda n naught e raised to the power minus lambda t. Let lambda n naught equal to r naught. R is equal to r naught e raised to the power minus lambda t. Here, r naught is the decay rate at t is equal to 0 and r is the decay rate at any time t. The rate of disintegration of a radioactive element is called its radioactivity or simple activity. It is denoted by R. Activity can be expressed as R is equal to n lambda. The SI unit for activity is becquerel. 1 becquerel is equal to 1 BQ is equal to 1 decay per second. Radioactivity. The time interval t½ during which half of the nuclei in the sample decay is called half-life. t½ is equal to N2 by lambda, which is equal to 0.693 by lambda. The mean or average life of a radioactive material is tau, which is equal to 1 by lambda. Example: carbon has a stable isotope carbon-12 and a radioisotope carbon-14 present in the ratio 1:1.4 into 10 raised to the power minus 12. The half-life of carbon-14 is 5,730 years. Find the activity of 1 gram of carbon sample. Avogadro's number is equal to 6 into 10 raised to the power 23. Solution: the number of atoms in 1 gram carbon is equal to 6 into 10 raised to the power 23 whole by 12, which is equal to 5 into 10 raised to the power 22. The number of carbon-14 atom in 1 gram carbon is equal to 1.4 into 10 raised to the power minus 12 into 5 into 10 raised to the power 22, which is equal to 7 into 10 raised to the power 10. Hence, activity of the sample R is equal to lambda n, which is equal to 0.693 by t½ into n, which is equal to 0.693 into 7 into 10 raised to the power 10 by 5,730 into 365 into 24 into 3,600, which is equal to 0.26 per second per gram. Approximately 16 per minute per gram. Alpha decay. Alpha particle is nucleus of a helium atom having atomic number 2 and atomic weight 4. It is denoted by, therefore, when an alpha particle is emitted from a radioactive parent atom X, its atomic number is reduced by 2 and atomic weight is reduced by 4. It can be demonstrated as the energy Q released in this process can be obtained from Einstein's mass-energy relation. It is given by the equation Q is equal to mx minus my minus mhe into c square. This energy is shared by the daughter nucleus and the alpha particle. For example, beta decay. A nucleus with an overabundance of neutrons can transform to a more stable nucleus by emitting an electron or a positron. This kind of process is known as beta decay. This process of beta decay can be expressed as where is the beta particle and is the antineutrino. For example, in some artificial disintegration, positrons are also emitted from the nucleus. Antineutrino and neutrino both are massless and chargeless particle and is emitted to conserve energy and momentum. Gamma decay. To explain the emission of gamma rays from nucleus, it is assumed that a nucleus possesses certain discrete energy states. When an alpha particle or a beta particle is emitted from the nucleus, the residual nucleus is left in an excited state. The excited nucleus returns to ground state by emitting a gamma photon, whose energy is equal to difference of energies of two nuclear states. For example, cobalt nucleus with mass number 60 and atomic number 27 transforms into nickel nucleus with mass number 60 and atomic number 28 in its excited state. The excited nickel nucleus with mass number 60 and atomic number 28 returns into ground state by emission of two successive gamma photons of energies 1.17 MeV and 1.33 MeV. Nuclear energy. Changes can occur in the structure of the nuclei of atoms. These changes are called nuclear reactions. Energy created in a nuclear reaction is called nuclear energy or atomic energy. Fission. The splitting of a heavy nucleus into two lighter nuclei is called the nuclear fission. When a slow neutron strikes a uranium-235 nucleus, it is absorbed by the nucleus and an unstable isotope of uranium U-236 is formed, which immediately breaks into two fragments emitting 2 or 3 neutrons with release of enormous amount of energy. The reaction may be expressed as nuclear energy. A chain of reaction refers to a process in which neutrons released in fission produce an additional fission in at least one further nucleus. This nucleus in turn produces neutrons, and the process repeats. The process may be controlled, that is nuclear power, or uncontrolled, that is nuclear weapons. Controlled chain reaction. If the chain reaction is arranged artificially, such that out of 2 or 3 neutrons produced per fission, on the average, only one neutron causes further fission, so that the rate of fissions may remain constant. Then the chain reaction is said to be controlled. Uncontrolled chain reaction. In this process, out of 2 or 3 neutrons produced per fission, on the average, more than one neutron cause further fission, and so there is no control on fission process. Thus, this is a very fast reaction, and huge amount of energy is released in a very short duration, and takes the form of a violent explosion. Thus, this energy is harmful and forms the principle of atom bomb. Reproduction factor. It is defined as the ratio of rate of production of neutrons to the rate of loss of neutrons. For chain reaction to take place, the reproduction factor should be greater or equal to 1. If the value of reproduction factor F is 1, the chain reaction is said to be steady. Nuclear reactor. Nuclear reactor is an important device which is based on controlled chain reaction and is a source of nuclear energy utilized for useful purposes. Fuel, made up of heavy atoms that split when they absorb neutrons, is placed into the reactor vessel, basically a large tank, along with a small neutron source. The neutrons start a chain reaction where each atom that splits releases more neutrons than cause other atoms to split. Each time an atom splits, it releases large amount of energy in the form of heat. The heat is carried out of the reactor by coolant, which is most commonly just plain water. The coolant heats up and goes off to a turbine to spin a generator or drive shaft. So basically, nuclear reactors are exotic heat sources. Production of plutonium. Some fast neutrons produced in the reactor are absorbed by uranium-238. As a result, it is converted into an unstable isotope, uranium-239. Uranium-239 emits a beta particle and is converted to neptunium-239. Neptunium also emits a beta particle and is spontaneously converted into plutonium-239. Nuclear fusion, energy generation in stars. The phenomenon of combination of two or more light nuclei to form a heavy nucleus with release of enormous amount of energy is called the nuclear fusion. Now we consider two deuterons to form a tritium. The tritium so formed can further combine with a third deuteron to form an alpha particle. The net result is most of the liberated energy appears in the form of kinetic energies of protons and neutrons. Controlled thermonuclear fusion. The combination of atomic nuclei at high temperatures to form more massive nuclei with the simultaneous release of energy. Thermonuclear fusion is the power source at the core of the Sun. Did you know? Anil Kakodkar is an eminent Indian nuclear scientist. He said, nuclear power is actually as safe as air travel, even though people perceive it as dangerous. Kakodkar also said that the catastrophe syndrome, which accompanies the word nuclear plant, needed to be put in perspective, especially to population groups and civil society activists who have been opposing nuclear power in India. Summary. Let us summarize what we have learnt. Atomic mass is conventionally expressed in atomic mass units. 1 atomic mass unit, or EMU, is equal to 1.6605 into 10 raised to the power minus 27 kilogram. Every atomic nucleus contains basically two types of particles, protons and neutrons. The radius of nucleus R is given by, where R0 is equal to 1.2 into 10 raised to the power minus 15 m is a constant, and A is the mass number of the nucleus. Einstein mass-energy equivalence relation, where energy E is equivalent of mass m. C is the velocity of light in vacuum, that is 3 into 10 raised to the power 8 meter per second. The mass of a stable nucleus is less than the total mass of its nucleons. This difference delta m in mass is called mass defect and is given by the energy equivalent to the mass defect, that is delta m, into c square is the binding energy, Eb, of the nucleus. Nuclear force is the force which binds the nucleons together and is responsible for the stability of nucleus. The decay rate can be expressed as, here, R0 is the decay rate at T is equal to 0, and r is the decay rate at any time t. The rate of disintegration is called activity. It can be expressed as the SI unit for activity is becquerel. The time interval t½ during which half of the nuclei in the sample decay is called half-life. The mean or average life of a radioactive material is the splitting of a heavy nucleus into two lighter nuclei is called the nuclear fission. The phenomenon of combination of two or more light nuclei to form a heavy nucleus with release of enormous amount of energy is called the nuclear fusion.